Now we are moving into, for dynamical systems, transfer function is defined for linear time invariant systems. It is the ratio of Laplace transform of output to Laplace transform of input with zero initial conditions. Consider a series RL circuit. We have seen the differential equation governing this system is this. So if I is considered output and V is considered input, the transfer function is nothing but I of s by V of s is given by this particular value, L by s plus R by L. So this is for linear systems. What if it is a non-linear dynamical system? So as usual, at steady state, y naught is equal to x naught square, because at steady state this y dot value will become 0. So at a particular equilibrium point, y naught is equal to x naught square. How to linearize this non-linear dynamical system? So as explained in the previous video, consider a small perturbation in x and small perturbation in y. So wherever y appears, replace y naught plus delta y, and wherever x appears, replace x with x naught plus delta x. So if we zoom the response of this nonlinear system around that operating point, around that perturbations, around that small perturbations in the closed neighborhood, it is a linear system with respect to those incremental changes. So when we replace y with y naught plus delta y naught dot, since y naught is constant, its derivative vanishes, so we will have only delta y dot, and y naught plus delta y and x naught plus delta x whole square. On expansion, x naught square plus 2x naught delta x plus delta x square. If delta x is small, delta x square is very small. So y naught and x naught square get cancelled. So delta y dot plus delta y is 2x naught delta x, or the incremental transfer function delta ys by delta xs is given by k by s plus 1. The value of this k is the differentiation of the nonlinear part with respect to x at x is equal to x naught. So what is the nonlinear part? It is x square. So we have to differentiate the nonlinearities with respect to input and output variable, but we are not seeing whether this dynamical system is a linear function of time or not. We are interested in finding the linear approximation of this nonlinear system at a particular operating point, which is nothing but incremental transfer function. So how to do is find out the nonlinear part, differentiate with respect to x, and substitute that operating point. We will get that constant. So this will be your linear approximation or incremental transfer function of a nonlinear dynamical system.